All right, so suppose we are tasked with making a bin. So this is like a box with no top. So it's gonna have, front, sides, and back, and a bottom. But the top is gonna be open. And suppose we want it to have a capacity of 4, so it has to have a volume of 4. What dimensions will minimize the amount of material required? So we have, on the one hand, surface area, and so the surface area for this is going to be, let's see, so we have the let's call it S, and X, Y, and Z will be the side lengths of the box, and so we're going to have the bottom, which will be X times Y, length times width, and then we'll have this the sides 2 times XZ and 2 times YZ. So this is the left and right sides, and then this is the top and bottom. Okay, and so this is the thing that we are trying to minimize. So this is going to be our objective function. And then we want the volume, and the volume of X, Y, Z is just X times Y times Z. We want that to be fixed equal to 4. So that's our constraint. Okay, so we've got our constraint optimization set up, ready to rumble. Now, I guess one thing to notice is that this just sort of before we get into it, is that the surface area function here, this guy, there are no extrema of this function on R3. We can make this as big as we want by taking X, Y, and Z as big as we like, or as small as we want by taking X, Y, and Z to be as small as we like. So, so there are no maxima or minima on R3. However, if we constrain it, so when we constrain it to the level set, the level surface actually, where V is equal to 4, then we will find that there are constrained extrema. Okay, and to give you a bit of an idea of what this looks like, let me bring in some plots. Here's a plot of some level surfaces of S. So this on this surface right here, this is actually where S is equal to 16, and then this one here is where S is equal to 9, and then where S is equal to 4, and then where S is equal to 1. And you can tell we can make the surface area as small all the way down to 0 if we like, just by taking X, Y, and Z sufficiently close to 0, right? Meanwhile, over here, we have the level set where V is equal to 4. It looks like basically a corner of a rectangular solid that somebody sanded off a little bit and sort of rounded out around where the origin is there. So, okay, now if we actually combine these two together, then you can see that what's going on is we've got so here's now the intersection of these. So you can see that the level set for where S is equal to 16 is all around. Oh, that purple doesn't really show up so much. Let me try green. How about that? Okay, there we go. Is all around here. If we move down to the one where the level set is at 9, it doesn't intersect it at all. Actually, it's out past it here. So that tells us that the so like if you imagine the value of S decreasing from 16, 15, 14, etc., it's going to be making these smaller and smaller sort of swoopy triangle things until somewhere it like hits, and there's going to be that last surface that just tangentially touches it at a single point, and that point there, that's going to be our constrained extremum. That's going to be the smallest surface area, so the level set of the surface area function corresponding to the smallest value that is still touching the constraint on the volume there. Okay, so that's what it looks like conceptually and geometrically. Now, how do we go ahead and solve this? Well, the idea is to solve the constraint for one of its variables. And so this one's pretty easy. I can just subtract or divide the xy over to the other side and write it as z equals 4 over xy. And then we're going to substitute into the objective function. So we're going to, so let's see, so we started off with sxyz equals xy plus 2xz plus 2yz. And then when we substitute that in, we're going to get, I'm going to call this little s just to differentiate it, because it's now a function of only x and y, and it's obtained from the big one by doing this substitution. So if I put 4 over xy in for z everywhere it appears, let's see, so we've got xy plus 2x and then 4 over xy, and then we've got 2y 4 over xy. Yeah? And so our new sort of, let's call it the constrained, I'll make it purple because it's fancy, constrained objective function is just a function of two variables. And it's, what is it? So we've got xy plus 8 over y plus 8 over x. All right. And so now let's see. So now we optimize this new constrained objective function, and we do that with first derivative test. So let's see. So the gradient of little s is going to be, and so we take the first partial with respect to x, and we get y minus 8 over x squared, and we take the first partial with respect to y, and we get x minus 8 over y squared. And then we set this equal to 0 for the first derivative test, and that gives us a pair of equations. So we have, we get xy squared, I guess I should put this square, x squared y equals 8, and xy squared equals 8. And let's see, so now I can solve for y and then substitute that in the other equation, and we end up with x 8 over x squared equals 8. And let's see, so then doing some mucking around with the algebra, we get 8 equals x cubed, and then that tells us that x is equal to 2. And then if x is equal to 2, we can substitute that one back over here to find that y is equal to 2 also. So we have 2 is a critical point. And if we punch that into the function, we see that 2, 2, 1, because when x is equal to 2 and y is equal to 2, then our constraint right here is going to tell us that the z coordinate has to be equal to 1. So this guy is a constrained critical point of capital S. That earlier one was of little s. And so that's going to be the optimal box. So it's going to be 2 by 2 and then 1 tall. A quick reality check, that does indeed have volume 4, so that's good. And let's see. So there are also critical points where x is equal to 0 and y is equal to 0. If you'll notice, those also will would have worked because they correspond to the situation where the partial derivatives do not exist. But we can rule those out by reasons of reality. We don't want to have a box that has side length 0. And even beyond that, it would violate the constraint that the volume is supposed to be equal to 4.